You let me know when we start. We start in 2 minutes, I guess. Yes. Okay. Jespal, should we start or should I wait a bit more?
Yes, sir, we can start. I will again put up one message in the group to join everyone. We may
We
start in
wait.
one
I
minute.
can wait. Yeah, 2 more minutes.
Uh, Hello, sir. Sir, we may start.
Okay, perfect. Are you recording or?
Yes, sir. Now recording part is done by my another team. So,
Okay,
because when
perfect.
I start, my system gets very slow down. So I am not recording now. They are
Okay,
taking care
perfect.
of recording.
Good. All right, so welcome back, everyone. I hope that you're well. Let's continue from where we left yesterday. Excuse me. Just let me quickly recall one or two things we said yesterday. So we studied the scalar denoising problem, which is a very simple inference problem, which is just about denoising a scalar signal x star, a scalar variable x star, which is corrupted by additive Gaussian noise, and therefore the data, which is a single number, is our signal times the square root of the signal to noise ratio plus Gaussian noise, okay? Which is equivalent, of course, to say that y, our observation, is just drawn from a Gaussian variance is 1, and we're trying to recover the mean, essentially x star, okay? And what we've seen is that we can derive the IMMSE formula. I mean, I haven't given the details there, but this is your job to check at the proof. It's not complicated. But with the final formulas for the MMSE, which are explicit for the Gaussian and Rademacher case, for example, for the Rademacher case, this is the formula for the MMSE as a function of lambda. We can draw this MMSE, the best error you can achieve in this reconstruction problem, as a function of the SNR. And what we've noticed is that the curves are not so interesting. There are no non-analyticity, no discontinuities, nothing very interesting happens. It's just a smooth decreasing curve in both cases, with the Rademacher curve being below, because the Rademacher prior is, of course, a more informative prior than the Gaussian. It constrains more your signal, okay? Perfect. So what we said is the reason why these curves are not so interesting is because there is no complexity. What we need is to consider inference problems where we aim at reconstructing a large number of parameters. So we want to be in the high dimensional setting. And these unknown parameters should somehow be coupled, should depend on each other through our observations. And this is where the Spike-Wigner model enters. So in the Spike-Wigner model, every observation is about not anymore a single component of a vector, but it's about two components. It contains information about two components, and therefore it introduces a coupling, because each observation is a function of two components, and therefore you have dependencies. So it's the product of two components of our unknown vector, xi star, xj star, multiplied by the signal to noise ratio square root lambda, divided by square root of n. I will say why this square root of n is important, plus Gaussian noise, okay? And the inference task is given all these pairwise measurements, these yij's for every I less than j. Can you reconstruct x star, which you do not know, and of course you do not know the noise z as well. You just know the functional form of these observations. You know that yij was constructed in this way, but you have to reconstruct x star, okay? Perfect. So we will see in this lecture that this 1 over square root of n is important. The reason basically is that this is a matrix that we call a Wigner matrix. We will study it today, and it has a certain spectral norm. So basically its spectrum of eigenvalues has a certain support, and somehow this scaling there is such that this matrix, which is a rank 1 matrix, concave as a function of the SNR. And for such sequences, the limit and the derivative obtained by solving this consistency equation. And this is just a scalar given square root lambda q x star plus z. Okay? So you solve this consistency equation. Maybe there is only one solution, then you pick it. Maybe there are more than one solution, then you need to find the one that minimizes this potential, this function. And once you pick it, you plug it in this very simple formula, rho squared minus q0 squared, and you have access to the MMSE. So now we have an explicit formula for the best error, the best reconstruction error, the base optimal reconstruction error on this rank 1 spike. Okay? So you can try any algorithm in the universe, whether it is efficient or it takes infinite time to run because you want it to be as precise as possible. You cannot beat this mean square error. This is the best you can do because this is the best estimator that exists. It's the Bayesian estimator. We have proven by Bayesian decision theory that is the best. Okay? Okay. So I will move on. If there are no questions, if there is a question, just ask me. Okay.
Yes, sir. I have a question.
Yes. Go ahead.
Last statement like this one. So I wanted to know, like, for each and every time, like whatever we are the theorem or the formula we are using, like for this limit and tending to positive infinity 1/n². So like how the algorithm works for the infinity terms, because there should be kind of a limiting parameter, like using infinity itself. uh, there, there must be a parameter so that will limit the constraints and the noise and each and everything. So that's what I am wanted to get know from this, like how can we understand this?
I'm sorry, your question is not very clear, but what you mentioned is algorithm.
Yeah.
Here, what I'm saying, there is no algorithm. What I say is a theoretical result. Of course, we are considering these infinite size limits. So this is purely a theoretical result, right? So in practice, so I want to say two things. The first thing you see is that I'm taking limits when the system size grows. So conceptually, what I'm saying is that I'm considering the inference problem for a certain size. Then I increase the size, kind of regenerate an instance of this spike-Wigner model, but of a slightly bigger size. So I have more unknowns and more data, which are both controlled by n. And I do that for n, which is increasing. And so I'm considering a sequence of problems, okay? And I'm studying how, what is the mutual information and the MMSE for this sequence of problems when the problem size becomes very large, and it's given by this, okay? In practice, this is of course not the case. In practice, you have the problem, which is for a given size, let's say n equal 1000, and that's it. You have the data in your hand, and you cannot increase or decrease the problem size. You cannot do anything. You just have the data, and you want to make inference, right? So how do the two relate? The point is that what you can prove in this type of problems, very generically, is that you have so-called concentration. What does it mean? It means that if for a given size, a finite size n equal to, let's say, 1000, which is large but not too large, it's realistic. You're trying to solve the spike-Wigner model with an actual algorithm, okay? And you compute the error. Let's say you're doing this in a theoretical setting where you have access to the unknown parameters just to compare with your estimator. You're making an experiment. And you compute the error that your algorithm obtained. And you compare this to this quantity, which is instead the error predicted for the infinite size limit. They will be very close. This is what concentration means. It means that this quantity without the limit, so for a given n, even without the expectation, you can remove the expectation. This object, which is really the concrete, the explicit minimum mean square error for your problem, will be very close, and by very, I mean with an error that is of order 1 over n or something of this sort. It will be very close to this object, which is the theoretical prediction, where we took an expectation with all possible realizations of the problem, and we took also a limit when n is infinity. But somehow the finite size version of this object and the infinite size theoretical prediction will be very close when n is not small, okay? So this is why this kind of asymptotic formulas are useful also to understand concrete, practical, finite size problems. It's what we call concentration, okay? I hope it answers your question.
Got it. Yeah, thank you.
This is a very important point. Thank you for asking. It was I should have mentioned that earlier, because for me it's something a bit obvious, but of course it is far from being obvious. I will mention that point more. Okay, so now we have these formulas. Let's exploit them and draw what we call a phase diagram in physics, okay? Phase diagram is, maybe you've not heard about phase diagram if you haven't studied physics, but you've seen phase diagrams if you come from electrical engineering, from most of you have seen somehow versions of phase diagram. They were just not called phase diagram. It's just how physicists call it. It's just a figure that tells you as a function of what we call a control parameter. The control parameter here is the signal-to-noise ratio. So the control parameter is somehow a quantity you should imagine that in a experimental setting is something you can tune, you can control, okay, and change and see how the problem behaves as a function of this parameter. And the object that you are interested to analyze, to understand as a function of this control parameter is called in physics the order parameter. It describes the problem. And the order parameter is in the context of inference is the mean square error. It's the reconstruction error that quantifies how good is your estimator for the unknown parameters. Okay? So phase diagram is plotting how an order parameter, the MSE, changes as a function of the control parameter, the signal-to-noise ratio. And with these replica formulas, now we can plot explicitly the MSE as a function of lambda. And what happens, so forget this at the moment, I will explain it later today, is this picture. It is really the main conceptual point of all this course is to understand what this means, okay? Because here, this phase diagram is plotted there for the spike-Wigner model, but what I'm going to describe now is extremely general for high-dimensional inference problem, for high-dimensional learning problems in machine learning. It's a very generic picture, okay? The exact values where this, the exact value of these curves or the exact value at which they change like this, of course, is problem dependent. But the presence of these different regions that I'm going to describe now is very generic, okay? Okay, so let's see what they mean. So I'm plotting three curves. The first curve in black is characterizing the performance of the Bayesian optimal algorithm. Okay, this is what I mean here. So this is the minimum mean square error performance. So this black curve is the best error that any algorithm can reach. It's the information theoretic bound, okay, on the performance. The blue curve, dashed, will be the performance of a practical algorithm that you can use for a given problem, and we're going to study today. It's called spectral PCA. PCA is for principal component analysis. This is a spectral algorithm in the sense that it will be based on diagonalizing the data matrix and looking at its eigenvectors. So it's based on the spectral decomposition of the data. And the third in red is a Bayesian algorithm, like the optimal algorithm. The optimal algorithm is essentially computing the posterior mean, which is fully Bayesian. This is also a Bayesian algorithm, but which is trying, therefore, to compute the posterior mean, but not by brute force. It's trying to compute the posterior mean in a computationally efficient way. Instead, you see, what do I mean by brute force? Brute force, so the posterior mean, to reconstruct the spike. So the base optimal estimator is this. And this concretely is an integral over R to the n, which is the dimension of our vector, of x transpose, which is an n by n matrix, of the posterior distribution of x given y, which we wrote before for the spike-Wigner model. And you need to integrate over x. So you see, this is an integral over a very high dimensional space. So you would need to sum over a volume that grows exponentially with n. And this takes forever, of course, when n is large. You cannot compute this integral explicitly. There is no way, right? Maybe you can approximate it by doing Monte Carlo. You can use smart algorithms, but these are algorithms. Maybe they work, maybe they don't. Computing this exactly is in general not possible, okay, due to this high dimensional integral. But if you were doing so, information theory tells you that you would get this performance in black, okay? We computed this through theoretical tools when n is large. instead, the red curve, this Bayesian algorithm called AMP, that stands for approximate message passing, is trying to approximate this expectation as an estimator, but not through a Monte Carlo, not by sampling this space. It's doing something else that we're going to discuss a bit. And you see that it has another performance which can match the base optimal one, but it requires a bigger signal-to-noise ratio. There is a region there where they do not match. So let's discuss these regions. The first region is called statistically impossible, in the sense that even the best algorithm in the universe leads a very poor performance. So let's say that this is 1 here, is the highest possible mean square error. This is the trivial error that you get if you always output the all zero vector. So it's the most stupid algorithm that exists. And the base optimal algorithm is matching the performance of the most stupid algorithm in the universe. It means that there is not enough information in the data matrix Y to say anything about the unknown parameters. So it is statistically impossible, and the statistically emphasize here that it's not a computational barrier. It's really a fundamental lack of information in the data to recover the unknown parameters. Okay? It's information theoretically impossible to recover the parameters in these regions, in this region of signal-to-noise ratio. Here the SNR is too small. So the inference problem in this region is doom. You cannot do anything, okay? Then, if the signal-to-noise ratio becomes bigger than this threshold here, that we call the lambda IT for information theoretic, it's called the information theoretic threshold, the MMSE starts being non-trivial. It's not 1 anymore. It's something smaller, okay? And you see that here the transition between at this threshold in the curve is discontinuous. So now we have a discontinuous behavior. You remember in the denoising problem, as a function of the SNR, the curve was very boring. It was this curve. Okay? No discontinuity, nothing interesting. Now we have discontinuities and interesting behavior that we call phase transitions in physics or threshold phenomena in computer science, because the problem is complex. You have interactions between many variables, and very concretely from the replica formula, what happens at this transition at the level of the formula we looked at, what happens there? You remember that the Q, the parameter entering the replica formula that allows us that we need to find the minimizer of it, that we need to plug in this replica symmetric potential, this function, to find the mutual information and the MMSE. This Q0, which is the minimizer, was given by this consistency equation. So you try to solve this equation, and basically what happens is that here the only solution is Q0 equals 0, which implies that the mean square error is 1. And here this Q0 is still a solution, but there exists another solution, which is the one minimizing this replica potential, this function you need to minimize. So you see, it's like if you have a function which is this replica potential. Let's call it IRS for replica symmetric, and the same notation that I used, of Q. And it looks like this. In this region, it has a single minimum at Q equals 0. And so it's the only one, you need to pick it, and it gives MMS equal to 1. But in this region, at some point, when you approach this SNR, because it's also a function of lambda, but here I'm plotting it as a function of Q at given lambda. When you approach this value of SNR close to the IT, it starts to have a second minimum that appears, a local minimum, okay? But it becomes the global minimum, so it goes down as Q, as lambda increase. And at some point, this local minimum becomes the global minimum, exactly at this transition. And now you need to pick this value. This is the recipe of the replica formula. You need to pick the minimizer of this function. And so you see you have a discontinuity. You go from something which is strictly equal to 0, there, to something which is strictly above 0. This is how it generates a discontinuity in the behavior of this function. Okay? This is what we call in physics a first order transition. It's when the order parameter, the statistic of interest, has a discontinuous behavior as a function of the control parameter, here the SNR. It's called first order transition in the sense that the first derivative of the mutual information, which is the MMSE, is discontinuous. Okay? So this is how, even if somehow the high dimensional problem collapses to the study of a low dimensional scalar denoising problem, you can still have non-trivial behavior, discontinuities, because you need to solve this kind of self-consistency equation that can have multiple solutions. And at some point, you have an exchange between the minimizer, between two solutions. And so it induces a discontinuity. Okay? Okay. So what is now this region beyond this information theoretic threshold, where the minimizer of the replica potential becomes a Q which is not 0 anymore? It means you can reconstruct. This is a region which we call algorithmically hard. Why? Because this is a region where even if the minimum mean square error is not 1, so it means information theoretically there is enough information in the data to reconstruct the signal, the unknowns. We do not know any efficient algorithms that are able to do so. If we take the best algorithms we know, which are these two, they still give a very bad error equal to 1, as if you were still in this region. So they are not able to extract the hidden information in the data, even if it's present, but they cannot extract it simply because they are not smart enough. We believe that in this region, the only way to get such an error is to explicitly compute this integral, which of course takes a time which grows exponentially with n. So this is not efficient. When the computational complexity of your algorithm grows exponentially with the size, with the number of unknowns, it is said to be non-computable, not efficient. It's too costly. If it's not exponential, if it's polynomial in n, then the algorithm is said to be efficient. These are two polynomial algorithms. This is an exponential algorithm. This is exponential n, the complexity, while this is polynomial in n. Both. Okay, so this is a very, very important point. The presence of algorithmically hard phases. Okay, it's called a phase also, again, with the vocabulary coming from physics. This is a algorithmically hard region or phase. This is the same. Okay, beyond this information theoretic threshold. But at some point, if you continue to increase the quality of the data in the sense that the signal to noise ratio becomes larger, the signal part in the data becomes more and more strong compared to the noise, at some point you enter the so-called algorithmically easy region. What does it mean? As the name suggests, it means that now we have an efficient algorithm in the sense that the number of operations it needs to do to output an estimator is polynomial in the size, such an efficient algorithm is now able to match the performance of the minimum mean square estimator, which in general is exponential. Okay? So this is what we mean. With polynomial time, polynomial cost algorithm, we can match the performance of in general exponential time requiring algorithm, which is this one. So it's algorithmically easy to find the optimal estimator. Okay? And so here we see a difference between these two algorithms. We see that the spectral, the Bayesian algorithm AMP suddenly goes from very bad, from trivial estimation, which essentially always output the all zero vector, to perfect performance, in the sense of optimal performance, base optimal performance, again with a discontinuous transition. Okay, it's a sharp transition. Instead, the spectral algorithm, PCA, which is much simpler, we're going to discuss it, is also changing behavior at the same transition, but it's not optimal. It gives a non-trivial estimation, a non-trivial error. It's not one anymore, but it's not matching the base optimal performance. Still, it's an efficient algorithm that you can use. Okay? But if you have access instead here to this AMP algorithm, you should use it because it gives something much better. And we will see that the reason why these two algorithms do not give the same is that they're very different classes of algorithm. In particular, this spectral algorithm, PCA, does not exploit the prior knowledge about the distribution of X star. I haven't mentioned it, I'm sorry. Here, this picture is for a given prior of the signal. The Xi stars are drawn from a given prior. And this given prior is a sum of two Diracs. It's not Rademacher, it's different, but essentially these components can take just two possible values, A and B, with a different weight. If you choose A and B in the correct manner, you obtain this picture. Okay? The Bayesian algorithm, like this AMP and of course the MMSE estimator, they do exploit correctly this knowledge. Not of X star, of course, you don't know X star, but the knowledge that the entries of X star were drawn from this prior. So they exploit the correct prior. The spectral algorithm does not exploit the prior. That's the difference. So you lose, you pay the price in terms of performance. Okay? Okay, can I move on? So this is conceptually very rich, this picture. Is there something I should repeat? Okay. We started at what time? Jaspal, for how long have I been talking? An hour and 15 minutes, something like this, no?
Sir, the time for the lecture has completed. If you wish to continue for 1-2 minutes to wind up, we can, and then we can resume back in the another lecture that is scheduled, I think, at 2:30 p.m. today.
Yes. Okay. I think this is a good point to stop. I think the students have quite a bit to digest conceptually here. And we can continue later then. So the next lectures we're going to start. So let me just lay down the goal for the two lectures of today. I will try to give you some techniques we're going basically to analyze this blue line. We're going to analyze to provide tools from what we call random matrix theory to understand the performance of this first algorithm, PCA. So conceptually, what we've done now is to, we haven't analyzed, but we have discussed the optimal performance through Bayesian decision theory, and then I gave you the replica formula that we're going to derive in 2 days. But we discussed mostly this thing. This afternoon, we're going to discuss this thing, which is a concrete algorithm you can use for the problem, okay? And it will lead this performance, okay, instead of that one. So we're going to study this in a bit more detail, okay? Sorry, and I forgot to mention that one important point, the threshold here at which algorithms starts to perform well is of course called the algorithmic threshold, in contrast with the information theoretic threshold, where the base optimal estimator becomes non-trivial, okay? This is instead the threshold at which the best efficient algorithm becomes non-trivial. And in this case, the algorithmic threshold, of course, this may depend on which algorithm you're talking about, and in general it does. The best algorithm that we know for this problem is this AMP algorithm. So this algorithmic threshold is essentially the threshold of this AMP algorithm. But it actually also corresponds to the threshold of this PCA algorithm, because they become non-trivial at the same location. But in general, it could not be the case. They could have different algorithms, could have their own thresholds. And the threshold for the PCA algorithm is not called lambda PCA, but it's called BBP, for the name of Benahous, Baik, and Péché, 3 mathematicians that precisely studied the behavior of this algorithm, and as we're going to do this afternoon. Okay, so see you in what time do we resume? At 2:30 for you.
2 hours, after 2 hours.
In 2 hours. Okay, perfect. Goodbye.
Okay, thank you. I thank Dr. Jan Barbier to spend the time, and I thank all the participants. So I hope, is there any questions? I shared the PDF also in the group yesterday, and also we are having YouTube live link also, that I have shared. So with these words, I again thank Dr. Jan Barbier and all the participants for patient hearing, and we will join back at 2:40 after 2 hours now. Okay, thank you.
Yes, see you.
Thank you.
Hey Jospal, should I start or?
Yes, I welcome you back, sir. So, yes, participants are joining. We are 15. Yes, we may start. In meantime, everyone will join.
Okay, but let me understand. I think that there should be more students. From what you told me, there were 40 something students. So how is it possible that only 14 students are online? 13 actually.
Yes, I think we can. Maybe we can wait. That all.
Yes, but it would be great if everyone is aware of the time. I mean, it seems that every lecture we have. Okay, I mean, yes. Okay. All right, so here is where we left the discussion this morning. We discussed the phase diagram of the problem, which tells us essentially how hard, let's say, how good can one reconstruct the hidden information, the spike given the data, as a function of the signal-to-noise ratio for a large instance of the problem. Okay, there was the region where it's statistically impossible to say anything about the signal. There is an algorithmically hard phase region beyond the information theoretic threshold where optimal estimation is giving something non-trivial, but efficient algorithms are stuck and are not able to extract the information. And finally, there is beyond the algorithmic threshold a region where we know an efficient algorithm which runs in a time which scales polynomially with the size of the problem instead of exponentially. And that is matching the base optimal performance. Okay. Again, can I ask some of the students to show themselves? I really have the impression to talk alone. I'm not even sure if people are there or not. I mean, it would be great if there is some level of interaction. I'm asking that at every lecture. It would be really nice. Thanks a lot.
Yes, I think maybe we all can on the camera, so it gives more sense of
Yes.
teaching learning experience gets more better if we see all the participants.
Yes, it would be great. Thanks a lot. Okay, so this picture is really fundamental. It's very important. And it's very general. So this kind of regimes with a statistically impossible inference phase, an algorithmically hard one and an algorithmically easy one applies to essentially all high-dimensional inference problems that one can study in modern data science. So this is really conceptually extremely important to keep in mind this picture. Sometimes the control parameter is different, has a different meaning. For example, in machine learning, the most natural parameter is not the signal-to-noise ratio. It could be the amount of data one has can access in order to train the machine learning model. Okay, so you would tune here the size of the training set, and you would track down how good is the model at generalizing on new data, let's say in a supervised machine learning setting, how good the model can generalize on new unseen data as a function of the amount of training data. And you would have a similar picture. There would be a regime where the model cannot generalize. There is not enough information in the training data to learn anything about the underlying rule behind the task that you're trying to solve. that connect input and output. There would be a regime where information theoretically you should be able to generalize correctly, but machine learning algorithms trained in a reasonable time are not able to achieve so. And then there would be a regime where the machine learning algorithm can learn. Of course, the picture can also change in the sense that depending on the problem, also, for example, depending on what prior you take in the current problem, this algorithmically hard phase can simply disappear, cannot be present. You could go directly from statistically impossible to algorithmically easy. It's a possible scenario. Another possibility is that there is never an algorithmically easy phase, and the problem is always hard to solve with efficient algorithms. You cannot solve them with efficient algorithms, even if information theoretically you can show that there is information in the data. This is another possible scenario. For example, if instead of considering the Spike-Bigner model, where you are trying to reconstruct a rank 1 matrix corrupted by noise, I'm dropping the signal-to-noise ratio here, you're considering, so this is a X tensor product with itself, this is the same thing. You're considering a tensor inference problem of higher order. So let's say that now Y is a tensor of order 3 and would be X tensor X plus Z. This kind of tensor problem have a different phase diagram where in particular this easy phase disappears. The problem is always algorithmically hard. So it is much more hard to detect, to find a rank 1 tensor hidden in noisy data, in a noisy tensor, than a rank 1 matrix. Okay? So component-wise, just to make sure that you understand what I'm writing, a tensor would be an object indexed by 3 indices, or 3, and its components if I want, of course. And the phase diagram as a function of the signal-to-noise ratio would be different. There would be no algorithmically easy phase. So the problem would always be hard. Okay? But what I mean by the fact that this picture is general is that you always have some of these phases. There's no statistically impossible phase. You could be in a case where as soon as the signal-to-noise ratio is non-zero, you can recover non-trivially the signal. Okay, this is also possible. Okay, so you have all possible scenarios, but it's always a kind of a combination of some of these phases: statistically impossible, algorithmically hard, algorithmically easy. Okay, perfect. So now the goal of the lecture now is to understand the performance of this spectral PCA algorithm that I'm going to explain now. Okay, so the spectral. So the question we want to answer is: can we provide a simpler inference procedure than computing the full posterior mean? Consequently, will be suboptimal because only the posterior expectation, the base optimal estimator, is optimal. But at least this procedure should be efficient. It should be computable always without requiring supercomputers, and you should be able to use it on your computer and see what it gives. And this procedure is given by principal component analysis. So basically, it entails computing first eigenvector of the data. So you diagonalize the data. It's a symmetric matrix. So you can diagonalize it. It will have real eigenvalues. and you can look at the eigenvector corresponding to the largest eigenvalue. And this is what I call by the spectral estimator, XPCA. Okay? So we want to understand how well this estimator, which is a vector, is aligned with the ground truth X star. Okay? Can I reconstruct non-triviality X star using the top eigenvector of the data? So to answer this question, we will need random matrix theory. Okay, so I don't know. These lectures will be self-contained, so even if you don't, I hope that you can get something out of it. Okay. So before trying to answer this question, I will define basic notion. Of random matrices. It was developed by Eugène Wigner, who was a theoretical physicist. And the original motivation for random matrices is, so random matrices are really what this large matrices, which are made of random entries. And we want to understand the statistical properties of such random variables, such random matrices. So Wigner was working on condensed matter, so they were trying to understand the properties of nuclei of matter, which are made of lots of protons, neutrons, electrons. And in quantum mechanics, these objects are described by Hamiltonians, which are energy functions, which are themselves large matrices. Okay, and these matrices encode all the interactions between all the components, the fundamental components of the atom or the molecule that you want to study. Okay, very large because these are very complex objects. There are many interacting components in a molecule, and so they are very hard to study. And typically, the question you want to answer in quantum mechanics is what we call the energy levels corresponding to a system of interest. Understand water, just one molecule. The basic question is to understand the energy levels, the excitations that this molecule can take. And mathematically, these are the eigenvalues. These correspond to the eigenvalues. So again, this Hamiltonian is this big matrix. And the problem is that these big matrices are so complex that you cannot analyze them directly. You cannot diagonalize very large matrices, okay? The complexity that it would require is too big in practice because these matrices are very large. And moreover, you cannot even write down explicitly these matrices. They're too complicated, okay? So the key insight of matrices and replace them by purely random matrices, okay, with very simple statistics, with, let's say, Gaussian entries. These are called Wigner matrices. And the hope is that there is the statistical properties that you can understand something about the true physical systems. Somehow you hope that there is universality in the sense that the precise details of a specific Hamiltonian do not matter, and that random matrices can capture statistical properties of these big, large matrices. It's so useful because you can model very complex systems by just studying idealized setting, which are just models between very simple variables. You're kind of the original problem. Nevertheless, the very fact of considering enough complexity, of considering enough particles that are interacting, even if the actual physics of a single particle is simplified a lot, you can still capture what is going on, because most of the things we observe in nature are emergent phenomena which simply follow from the complexity, from the fact that there are many interacting single elements together. But the details of how every single component behave is not relevant. It's not really relevant in the large system limit. In random matrices, this is the very same idea. It doesn't really matter what are the precise properties of like the atoms and protons and neutrons you're studying. That it says something about true physical systems. And yes, this is the case. Okay? Okay, so simple statistics, simple models of random matrices accurately predict various statistics of energy levels of complex quantum systems. The fact that it is interesting to study very simple models of random matrices by universality. And of course, here I've given you an application in condensed matter physics, which is the origin of RMT. But RMT, random matrix theory, is used everywhere now. So it's a main tool to study machine learning problems today, finance, to understand data in neuroscience, any field where you have large matrices, which means everywhere, random matrix theory is important. Okay, so it's a very important toolbox to know. So let me questions.
Yeah.
Question.
I have a question.
Yes.
Yes. So I was wondering, is the random matrix theory? So I've studied it slightly before, but your discussion just made the link. Is it related to 't Hooft's large N?
It's
dealing
related
with large matrices.
Yeah, I mean, I don't know really this expansion you're talking about. I've heard about it, but I don't want to say wrong things.
Of course, yeah.
I don't know. Maybe I can take a look. I would say that naively there must be somehow connection, because random matrix theory is always about large system limits, and one way to answer to study the analysis of the spectral PC algorithm is again through a kind of large N expansion. So
yeah, and
there's probably
it becomes like a mean field theory.
Yeah. I mean, random matrix theory is connected to mean field theory. Yes.
Okay.
Yeah. Thanks. Okay, so Giulio, for you, maybe what I'm going to say right now is a bit, these are known things, but I will nevertheless tell them. Hopefully what I'm going to say after may be new to you. Let's see. Okay. So the first, so in random matrices, we talk about ensembles. So we're talking about probability distributions over matrices. So the simplest case simple matrices. There are n by n symmetric matrices. Okay, let me call it H. And we say that H is a GOE matrix if its upper triangular elements are independent and are Gaussian. Okay, so the element ij of H, which I denote little hij, which is also equal to AJI by symmetry, is drawn from the Gaussian distribution simply for convenience. This is really a convention. In particular, this convention allows to write this statement in a more compact way, which is this. If this is an exercise, so all these H are Gaussians, and you can write this joint law, the joint law of all elements, meaning the law of the matrix itself, in this manner. Here I do not care about the normalizations with the 1 over square root 2 pi's, but you can write down explicitly this trace and you will realize that these are product of Gaussians. It's a product over the elements and you will recover this. Okay. And if you were putting something else than a 2 here, than a factor 2 between this and this variance, you could not write it in such a compact manner. And in particular, when you write the law ensemble of random matrices, is basically invariant in distribution to any rotation. What does it mean concretely? It means that if I take a H and I rotate it, so I rotate its eigenvectors from the left and from the right, so I change the basis, which concretely means that I apply an orthogonal matrix on the left and on the right of the matrix. Then let me write down its probability distribution. What's the probability of observing, according to the GOE ensemble, such rotated matrix? It is given by this, so it's the same as this, except that I apply O and O transpose on H. So I have my rotated H times my rotated H. Okay? And of course, because O is an orthogonal matrix, this disappears. And because of the cyclicity of the trace, I can move this O there without changing the trace. And so it simplifies again. So I recover the same probability weight. It means that any rotation of a GOE matrix has the same probability to occur as the original matrices. Okay? Okay, that's one comment to keep in mind. Okay. So, what is the most basic quantity you may wish to understand if you're studying large random matrices? The most basic statistic is the so-called spectral distribution or spectral density. Okay, so this is simply the empirical distribution of eigenvalues. So we're working with symmetric matrices, so all eigenvalues are real. They're not complex numbers. Okay, you could also extend everything I'm saying to the case where the matrices are not symmetric, the eigenvalues are complex, and everything generalized, no problem. But in data science problems, in the context of this course, studying symmetric matrices is enough, and they're even real. So eigenvalues are real. So I can define its empirical spectral distribution, which is the sum of delta functions at the locations of all the eigenvalues lambda I of H. Okay? So this is the empirical law of eigenvalues. This is essentially the histogram of eigenvalues, okay, for a given random matrix H, for a given instance, an outcome of the GOE ensemble, okay? Perfect. So one of the most fundamental and important results in, and one of the first historically in random matrix theory is the following. It's the so-called Wigner's semicircle law. It says that this empirical spectral distribution, and by empirical, I mean for a given matrix of a given size. Okay, so you sample a matrix from the GOE ensemble. So you have one matrix. It is, I don't know, of size 1000 by 1000. The elements are now fixed. They have been drawn from the Gaussian distribution. And you ask to your computer, give me all the eigenvalues, you plot them, you plot the histogram, and this is this distribution. So it's an empirical distribution. It's for a given instance. What Wigner has proven is that when the size of the matrix goes to infinity, so you consider an infinite sequence of matrices drawn from the GOE ensemble, drawn independently for each size, and you look at what happens when the size grows and grows. In the limit when the size goes to infinity, this empirical distribution tends to a well-defined limit, which is itself a probability distribution, which is called a semicircle distribution. That's why there is a S and a C here for semicircle, which looks like this, okay? And the formula is here. So it has zero mass away from -2 and 2. And between -2 and 2, it looks like a semicircle. That's the name, okay? And the formula is written there. So this tells you that even if, so you have to realize something. So we're considering a matrix made of Gaussian entries. A Gaussian is a probability measure that looks like this, right? So every element of the matrix Hij is drawn from a Gaussian distribution. So it has a distribution that looks like this, okay? Okay, but the support is infinite. So a Gaussian has a rather small probability to escape far away from the mean, but non-zero. A Gaussian can take any value from -infinity to infinity, right? But if you populate a big matrix with Gaussian entries, which each can go to plus or minus infinity, the eigenvalues become bounded. Okay, the eigenvalues in the large system limit cannot escape -2 and 2. Okay, and this is of course not a Gaussian law. So this is a more complicated law. Okay, so this is an important, very important result. So it describes the spectral density in the large size limit, what we call the asymptotic spectral density of symmetric Gaussian matrices. Okay. So you can already see the connection with the problem we're studying. This is telling us what is the spectral distribution of the noise in our problem, okay? So why is it interesting? Because you can already use this as a very simple statistical test, right? Because imagine that you have data that you model as a spike, a low rank matrix, plus Gaussian noise, so of the form of the spike-Wigner model, which again, I promise is actually a very general model. What you can do is simply, so the first question you may wonder is there some signal in this data? Okay, is there something else than pure noise? Okay. So to answer that question, you can simply do the following. Take your matrix of data, diagonalize it so that to obtain all the eigenvalues, plot the histogram of eigenvalues. You will obtain something like this. I don't know, the empirical histogram will look like this. Like this. And basically, if you do not observe any eigenvalue that are beyond, or of course for finite size, you may go slightly beyond plus and -2, but it has a very small chance actually. If your matrix is pure noise, it has a very small probability to happen. But if you don't observe any eigenvalue that are far away from this, what I call this bulk of eigenvalue, it's like this blob of eigenvalues, then with high confidence you can say, no, my data does not contain information, because basically this is what I should observe if my data would be pure noise. Okay. If, however, you observe something different, let's say that you observe additional eigenvalues, let's say one there, maybe one there, then you can say there must be something else than pure Gaussian noise, because random matrix theory tells me that if they would be only noise, I could not observe these eigenvalues. I could only observe this. But because I'm seeing this, it means that there's something else. So you can use random matrix theory as a statistical test in order to have a kind of null hypothesis to compare with, to detect whether there is a signal or not in your data. Okay? This is the null hypothesis. These are the eigenvalue distribution you should observe if there's nothing else than pure Gaussian noise in your data. Okay, and your data is if you observe something else, it means that there's something else. Okay, so this is very important. Okay.
Excuse me, sir.
Yes.
So you are saying like from this random matrix theory application, like if there is a lot of abundant same number of random datas or matrices are present in like in a space or anywhere, so we can detect the noise and the signal. Like we can differentiate between the identical matrices if there it is noise or signal. Like if what I'm trying to ask is, like if there is a copy of the same data, like there are a lot of data present in our surrounding and in system and everywhere, so like how can we distinguish? So is this the right method to distinguish random matrix theory and this GOE?
To distinguish in what sense? To distinguish what from what?
To distinguish like from like for example, like what I'm trying to ask is uh, uh, like say I have a data set of 1,000 people in a school, like okay, and the same data set is replicated or has just
of dimension n times p. So, and you can think of this matrix as where the rows, we have n rows, and each row is a sample, is a data point, which lives in p dimensions. P is the number of features. So the number of columns of this matrix is the number of features. You're observing p features n times. You have n samples of p features. Okay. So again, one natural question is, imagine that I have some matrix. Someone tells me that this is data, but I want to make sure that this is data in the sense that it's not pure noise. So what I can do is to construct. So now it's not a symmetric matrix. So I need to, the GOE does not apply. So I want to construct first the covariance matrix. The covariance matrix, which tells me how, so if I write down X, this is the covariance matrix. This is a matrix of size P by P. So this is the feature covariance matrix. Imagine that you have your data is a matrix of, you're observing the age, the sex, the blood pressure, some features for many people. Every person is a different sample. You measure many physiological features for all of them, and you want to know, for example, how dependent is the concentration of a certain chemical in the blood with the age. So what you can do is to compute the covariance between the two, the empirical covariance over the samples. So concretely, you are constructing this matrix there, X transpose X divided by N is the number of samples. And so natural question is, how would look the covariance, let's say the spectrum of a covariance, if my data is actually not data, it's pure noise. Okay, again, I want to have a kind of null hypothesis, something to compare with. So what you can do is, again, to study the simplest case where the matrix has Gaussian entries. Okay, X has Gaussian entries. You construct this empirical covariance of noise with itself. This is a V-sharp matrix. And so now you ask, what is the spectrum? Okay, again, all the eigenvalues are real, but now they're also positive because this is a positive semi-definite matrix, right? So, which means that all eigenvalues are positive. So, if you define gamma as the ratio between the number of features of columns in the matrix X divided by the number of rows, the number of samples, then the Marchenko-Pastur distribution appears. So the extension of the GOE of the Wigner result to empirical covariances of pure noise is the Marchenko-Pastur distribution. And it tells us again that as N and P go to infinity with a ratio gamma, the spectral density of a V-sharp matrix looks like this. So you can read the formula. It doesn't, it's not so important. It's a formula, but we can plot it. Okay. We can plot it for two different aspect ratios. So when gamma is 0.5, where again I recall gamma is P over N, the spectral distribution when P and N become very large will look like this, okay, in blue. So this is a non-trivial distribution. If gamma is 2, it will look different. It will look more spreaded, and also there will be a mass in 0 here. Because you see, the rank of this matrix, the rank of W is the mean between P and N. And this is a P by P matrix. So it means that if N is smaller than P, some eigenvalues must be equal to 0. Okay? And indeed, when this gamma equal 2, it means N smaller than P, some eigenvalues must be 0. The matrix is not full rank. And so you have a mass in 0. You have that many eigenvalues that are 0, gamma minus 1 over gamma. So this is a very important law, which again gives us a kind of null hypothesis, something to compare with empirical covariances of true data. So if you take real data, samples, features, you can write down the empirical covariance, then diagonalize it, look at the empirical spectrum of eigenvalues, and if it falls, if it's well described by the Marchenko-Pastor distribution for a given gamma, then you can say my data is basically rubbish, it's pure noise. If you observe something else, a deviation, a kind of important, sufficient, let's say a statistically significant deviation from this, you can say my data is not pure noise. Okay, it's something else. Okay?
Yeah, one quick question. But
yes,
if your matrices are so small, there could still be a major deviation, even though it's pure noise.
Of course. I mean, these are asymptotic results. This holds for P and N large. But let me just comment on this. Statistics such as spectra of eigenvalues for random matrices converge extremely fast to the asymptotic predictions, because much faster than if you're considering statistics of correlated random vectors. Because you see, somehow eigenvalues of a random matrix, another comment, even if the entries of the matrix are independent, like a GOE matrix, up to the symmetry, of course, but the entries of the matrix are independent. The eigenvalues are not independent of each other. They are strongly dependent, okay? And actually, the convergence of such statistics is extremely fast with N and P for V-sharp matrices in random matrices. So even, at some point I will show, even if you simulate a system of size 200, which is ridiculously, which is very small compared to practical sizes in modern applications, you can see that already the random matrix theory prediction is extremely accurate. Okay, so you really need to work with very small systems to have issues. Let's say, yeah. Okay, we'll do the simulations in the next lecture. Let me continue. Is there any other question, or okay? I will move on. So let me, of course, I cannot say everything, so let me just select what I want to say. I'm a bit slower than I expected. Yes. Okay, so what I will do, okay, I think I will first state the results, and if I have time, I will derive them. Which I'm not sure. So again, what's most important is that you understand the concepts. Then derivations is another thing. Okay, so now I want to make a bit more formal this description about using random matrix theory results as a kind of null hypothesis to be compared with in order to say whether there is information in the data or it is pure noise. Okay, so this is related to the spike-Wigner model. So what I want to tell you about now is one of the most, if not the most important threshold phenomenon, phase transition phenomenon in modern data science and in random matrix theory, which has deep implications not only in the spike-Wigner model, but I could cite applications in the training of neural networks, in detections of defaults in matter, in materials, in finance. I mean, it appears absolutely everywhere. Signal detection in large data sets of neuroscience experiments. It's really crucial. This phenomenon is called the BBP transition. BBP stands for Benarous, Baik, and Péché, who are three mathematicians who formalized this around 2000. Okay, so this is not so old actually. So again, the problem that we want to answer with the random matrix theory here is to distinguish the signal from the noise. Okay, so why is random matrix theory useful? Because random matrix theory predicts the properties such as eigenvalue distribution for pure noise random matrices, as I described, which can serve as a null hypothesis to compare with. Okay, so let's go back to the spike-Wigner model. The spike-Wigner model is almost like a GOE, except that there is a difference. We have a rank 1 matrix here. Okay, so here I'm redefining the spike-Wigner model just with different notations. You may wonder why. Simply because when working with random matrices, from the perspective of RMT, it is very convenient to work with matrices whose spectral norm, meaning the amplitude of the largest eigenvalue or singular value, is not increasing with the size of the matrix. So what I need to do is to divide by 1 over square root n, there is a typo here, my previous definition of the spike-Wigner model. So I'm redefining the spike-Wigner model like this, where D is our previous y divided by square root n. H, which is a GOE matrix defined as before, will be what I used to call Z divided by square root n. And the spike, U, is the old X star divided by n. You remember? So this is indeed y over square root n, which is indeed square root lambda X star over square root n. Before we just had a square root n there. Now I absorb it in this X star. I redivide by another square root n, which is this one, plus z over square root n. So it's the same model as before, rescaled. Okay? And this is what I call U, and this is what I call H. Okay? And square root lambda is what I call now tau. Okay? That's the mapping. But it's the same model as before. Perfect. So this results from Benarous, Baik, and Péché says the following. They have proven that the largest eigenvalue of the data, that I denote D for data, lambda 1, satisfies the two following properties. If the signal to noise ratio, or the signal to noise ratio, the square root of the what I used to call the signal to noise ratio, which is this tau. If tau is less or equal than 1, where 1 is here will end up being the so-called BVP transition, but so if tau is less or equal than a certain threshold, in this case 1, the largest eigenvalue of the data matrix tends to 2, which is also the largest eigenvalue of the noise only. It's the endpoint of the semicircle law. Okay? And this convergence is, of course, in the large system limit, when the matrices size become very large. If instead tau is greater than 1, lambda 1 tends to a non-trivial value, which is tau plus 1 over tau, which is strictly greater than 2. Okay, so what does it mean? It means that you have the semicircle law, which is, so here we're plotting the asymptotic spectral density, the asymptotic histogram of eigenvalues for the data matrix when n is very large. And we see that there is a big component which is related to the noise. Okay, it's the semicircle. But there may be an outlier, an eigenvalue that escape, as I've discussed before. And the location of this outlier eigenvalue is precisely tau plus 1 over tau. Okay? I will show you simulations. You will see that this is very precise. If you do simulations of this spike Wigner model and you diagonalize D, even for pretty small sizes, you will see exactly this picture, and the location of this outlier eigenvalue will be very close to this asymptotic prediction. Okay? Good. So this result tells us that there is a critical value of signal-to-noise ratio, this value equal to 1, which we call tau BBP, beyond which the signal becomes detectable. You can say, by comparison with the semicircle law, by looking at the eigenvalues only of the data and by comparing to the semicircle law, you will be able to say, beyond this critical value of signal-to-noise ratio, that there is indeed a piece of information in the data corresponding to a spike. Okay? Of course, the result generalizes if the low rank, the matrix you're trying to recover is not rank 1. It can be rank equal to 10, okay? And you will have multiple outliers at different positions. You will have 10 of them, okay? But the picture remains the same. So we can just focus on the case where we have just one, a rank equal to 1 for the signal, because it's conceptually nothing changes if you have a higher rank matrix, as long as this rank remains small compared to the dimension of the problem. So you have this outlier and you can say, yes, I can assess that I'm very confident that there is information contained in my data. Otherwise, I would observe only the semicircle. Okay? Perfect. So this is a phase transition phenomenon. Before tau equal 1, the top eigenvalue sticks to the endpoint of this bulk, and suddenly it escapes it, and it will go towards infinity as tau is increasing. Okay? It goes to infinity linearly with tau. Okay? All right, so the second result by BBP is the so-called eigenvector overlap. And this is what gives us the performance of spectral PCA. So what is this result telling us? It tells us that if you are beyond the BBP transition, so the signal-to-noise ratio is big enough to observe an outlier, the eigenvector V1 of the data corresponding to this outlier eigenvalue has a non-trivial overlap with the signal that you're trying to recover, okay? And you can compute exactly this overlap. The limiting value of the overlap squared, so here this notation, this is the inner product, so sorry, this bracket should be for an average over with respect to the posterior. This is not the case. Here this bracket means V1 transpose U. It's really the inner product. If you look at the inner product, which is a measure of recovery, of alignment between vectors, between your estimator, your spectral estimator, given by the top eigenvector of the data, and the hidden information, the U, and you look at the square, it is equal, in the large size limit, to 1 minus 1 over tau squared. Okay? So this gives us an explicit formula for the performance of spectral PCA. Okay? So this is how you get this picture, this curve in the phase diagram. Okay? And so you see that beyond lambda BBP, which is equal to 1, there is no information in the data that the spectral algorithm can exploit. So this is the region where basically the top eigenvalue of the data, so this is the histogram, this is for a real experiment, by the way, this is what I've simulated for n equal, I don't remember, maybe 500. I've plotted the histogram of eigenvalues of the data in the spike Wigner model. This is this yellow histogram. I've put on top the semicircle law. You see that it characterizes extremely well what you observe in practice. And I've indicated in red the location of the maximum eigenvalue. And you see that in this case, it is 2. So in this region, which is the statistically impossible and algorithmically hard region that lies before the BBP transition, the spectral estimator cannot give you anything, okay? But as soon as this top eigenvalue that you see is there, it really escapes, I'm not lying, escapes the bulk of eigenvalues related to the noise in the data, the performance of the spectral PCA becomes non-trivial. You have an alignment between the associated eigenvector and the hidden vector x star, which is u in our notation in the lecture today. Is it clear? Okay, so if there is a question, please ask. So this is the main result I wanted to explain in random matrix theory. So the next lecture I will try to, will not be able to do all the derivations I wanted to explain to you, but I'll do at least one derivation. Maybe I'll explain at least how to obtain the GOE, how to obtain this result. Okay, that's what we're going to do next.
Okay, sir. Do we have any questions? Okay, maybe take one screenshot with all cameras on, with all participants. I request everyone, if you can on your camera, we can take one screenshot. So, sir, do we end here?
I mean, it depends. If you want me to end there, I can, but I have many things to say. So, I mean, the more I speak, the more I can.
Instead of going for derivations, we can cover some parts in the next session after 1 hour we are having.
Perfect. Okay, that's fine. I'll explain some of the derivation in the next lecture then.
Okay, so if everyone is switching, everyone will switch on their camera. I may take 1-2 screenshots.
I think people really hate showing their faces.
Yes, I don't know why. Okay then, sir. I thank you. I thank everyone for the kind hearing, and we will join after 1 hour, right? So I request everyone to please join on time, because our team who is doing recording has also, they also need to go by 5:30. So we will start at 4:30 after 1 hour, exactly after 1 hour.
Okay, see you in an
They
hour
also
then.
leave on time. So I request every time Professor John Barbier joins on time, and then everyone I have to text. So I request all to please join on time after 1 hour. Okay, thank you, sir.
See you later.
Hello, sir. Good afternoon. In fact, good evening for us. So I welcome you all again, once again.
Hi. Let me know when to start.
Yes, I think we may start. Participants will be joining. And I again would like to request everyone, if you switch on your camera, we get more clarity and we understand more as a teacher that you are gaining something. So I suggest everyone, if you can switch on your camera, please. I will try to leave and join. I don't know, my camera is not working. Maybe I will restart my system.
No problem. Okay, so really no one wants to show themselves. That's fine. I can talk to a black screen. Thank you, sir, for your courage. Hi.
Hello. Yeah.
Okay.
Last year at ICTP for
Yes, I
youth and high dimension.
recognize you. Of course. How are you?
Good.
Where are you?
Right now I'm in Colombia.
Okay, okay.
Yeah, I used to be in Wisconsin.
What am I doing? Okay. All right, let's start again. So we discussed the basics of random matrix theory. I've presented the Gaussian orthogonal ensemble, which is the simplest random matrix theory model you can think of. It just represents symmetric Gaussian matrices. And we've seen that despite the simplicity of this model, rich behavior emerge for the eigenvalues, in particular the asymptotic spectrum of the eigenvalues tends to that of the semicircle, which I've shown here, despite the fact that the matrix elements are independent, the eigenvalues are not independent, they are strongly correlated, and their marginal distribution, meaning the probability distribution of one of them, which is really what this law is. This is if you want, this law really is the same this is the marginal law. So this is the integration, or this in the limit. This is the integration of the joint law of eigenvalues with respect to all of them but one. And it has this non-trivial behavior. Okay. Then we presented the V-sharp distribution, which is the next most important random matrix ensemble, which represents random covariances, covariance matrices, so covariances of pure noise. And in this case, the law is that of Marchenko-Pastur, and it is a law which is supported on the positive axis because covariances matrices are, of course, positive semi-definite. Okay. Perfect. And then we have discussed the BBP phenomenology. We have seen that when considering the Spike-Wigner model, meaning a rank 1 perturbation of a GOE matrix, we have an interesting phenomenology that appears, which is that if the signal-to-noise ratio is too small, is less than this BBP threshold, then we only observe the semicircle distribution for the eigenvalues of the data. Despite of this rank 1 matrix, which is not coming from the noise, which should participate, it is kind of absorbed by the noise room, and it is hidden by this bulk of eigenvalues, and you cannot say that there was a signal, a rank 1 matrix hidden in the data from the eigenvalues. And actually, you can show, we've seen the phase diagram at the beginning, that you are in the statistically impossible phase. There is no procedure whatsoever that, given the data, will be able to say anything meaningful about the signal. So this is really, this BBP transition excuse me, no, right now I'm saying something wrong. No, excuse me, there is, depending on the prior, there is potentially this hard phase, which is this region where you can say something potentially about the signal if you have infinite computational power, very large computational power, but efficient algorithms cannot do so.
Yeah, I was going to say, like, if you have a guess, a really good guess,
yeah,
for the signal, I mean, I guess
yeah,
that's exponentially close.
Yeah. So a good guess is a form of a prior. So if you, let's say, if instead of saying that your signal can be anything, you can enforce it to belong to a cone, so a region around some guess, of course, this picture will change. So this picture depends very much on what is your prior. For a given prior, which in this case is like it's a version of a Rademacher prior where you have just 2 Diracs, the picture looks like this. If instead this one I know it, if instead the signal is Gaussian distributed, which is a very weak prior because it's basically knowing that a vector is Gaussian tells you nothing about its direction because the angle of a Gaussian vector is uniform. The only thing that you know is essentially its norm. In this case, the phase diagram looks like this. The MMSE looks like this. And the lambda IT, the information theoretic threshold, is also the BBP transition. So this is for xi star, which are Gaussian.
Oh.
So in this case, there is only an impossible phase and an easy phase. So in this case, the hard phase disappears, and basically the BBP transition matches the information theoretic transition. Okay, so it means that when you have essentially no prior about the signal, which is essentially the same as saying that it is Gaussian, because a Gaussian prior is only a constraint on the norm, but nothing about the angle, which is really the angle is really the thing you don't know. The norm is a very weak constraint. So essentially having a weak prior about the signal implies that the BBB transition defines also the information theoretic transition. It means that as long as there is no outlier in the data, there is no way to extract the signal non-trivially from the data. However, if your prior is stronger, if your prior, let's say, is let's call this rho tau A plus 1 minus rho tau, sorry, not tau, excuse me, delta in A plus 1 minus rho delta in B. So you have a Dirac in A and B, and you tune this rho correctly, and A and B, you obtain this picture. So you can make a hard phase appear. Okay, so it depends on what's your prior. Okay, perfect. So now the question is, can we derive, what is the key idea to derive such a result? And what I'm going to show you is a very systematic approach which allows to derive spectral densities of many random matrix ensembles. And it consists of two main ingredients. The first is that we're not going to compute directly the spectral distribution. We're going to go through another object which is related to it, which is called the Stieltjes transform, which is somehow the moment generating function associated with this distribution. Okay, with this distribution, its limit. So we're going to work with the moment generating function instead of the density itself. And this is a usual trick in probability. It's often easier to obtain equations that characterize the moment generating function than directly probability distribution. And then you reconstruct the probability distributions out of it. So first thing, I'm going to define and work with Stieltjes transform. And the second thing is that I will show you how to obtain an equation describing the Stieltjes transform through a method which is called the cavity method. So, or a leave one out approach. In statistics, they call that the leave one out approach. In physics, you call that the cavity method, and I will tell you why it's called like this. Okay, so let's define. Again, you don't have to read everything, and just focus on what I'm showing. We need to define the so-called Stieltjes transform, and which is related to also the resolvent matrix. So what is the resolvent associated with the matrix? It's another matrix which has the same dimension. And so if I give you an n by n matrix H, which may come from the GOE ensemble or from any other ensemble, I define its associated resolvent, denoted capital G, that depends on an argument Z, which is a complex number, and it is equal to Z times the identity minus H inverse. And this inverse is in the sense of matrices, okay? And this Z can be any complex number apart from the eigenvalues of the matrix H. And indeed, you see that if I plug here an eigenvalue of this matrix, this object is not well defined. It will explode. Okay, there will be a pole. So here I'm removing the possible poles, but apart from that, Z can take any value. So this is a complex valued matrix related to the inverse of the original matrix. Okay. What I'm going to show you is that somehow this resolvent matrix is easier to work with than the matrix you want to study directly. And secondly, it contains somehow the same information. Okay, you can extract the spectral density of H and properties about its eigenvectors and all that directly from the resolvent. Notice actually that this resolvent matrix, which by the way we call resolvent because it allows precisely you to resolve many problems using it. The resolvent has the same eigenvectors as H, right? Because if I add a matrix proportional to the identity to a matrix, I'm not changing the eigenvectors. So this Z identity minus H is just a constant shift by minus Z of all the eigenvalues of H. And then I'm applying the inverse, and the inverse operation is like doing the inverse of the eigenvalues, but the eigenvectors are untouched. Okay? So if I do the spectral decomposition of H as sum of lambda I, VI transpose, where VI's are the eigenvectors of H, then GH of Z is sum of VI transpose, same eigenvectors, but the eigenvalues have been shifted. Okay? This is this matrix. Perfect. So now that we have this matrix, I can define the resolvent. The resolvent is simply the trace of this matrix of, sorry, the Stieltjes transform is the trace of the resolvent divided by n, so that this has a limit when n goes to infinity. This remains of order 1 when n goes to infinity. You can think of this 1 over n times trace as like an empirical average. I'm averaging over the diagonal, or equivalently over the eigenvalues. Of course, the trace is the sum of the diagonal elements, but it's also the sum of eigenvalues. So I'm doing an empirical average of the eigenvalues of this matrix, and I take an expectation over the law of this matrix, which could be a GOE matrix, and I take the limit, okay? And this can be written equivalently, so I ask you to check this equality, but this should be direct. This can be written equivalently as an integral over the spectral density, the asymptotic spectral density of the matrix H of Z minus lambda, okay? So this, check it, but it should be direct, okay? So you see, again, this is an empirical average over the eigenvalues, and this is indeed, this operation is an average over the spectrum, and the function that I'm averaging, the eigenvalues of the resolvent are indeed 1 over Z minus lambda I. So here I'm doing the average of Z minus lambda with respect to the empirical spectrum. So these two quantities are indeed the same. Okay? So this is a definition. This is the Stieltjes transform. Stieltjes was a mathematician. Perfect. So why is this a nice object? Because we will see that it's easier to derive an equation for the Stieltjes transform rather than for the spectral density directly. And the second thing is that they're one-to-one connected. Okay, if you know one, you know the other, and vice versa. In particular, the Stieltjes transform is the moment generating function associated with the spectral density. So what does it mean? It means that if I take the derivative of the Stieltjes transform with respect to 1 over z, the k plus 1 derivative with respect to 1 over z, and I look at this derivative around z going to infinity along the real axis, because z a priori can be any complex number, then I obtain k plus 1 factorial times the kth moment of this probability distribution, right? This is the definition of the kth moment. This is mk, right? It's the expectation with respect to the spectral distribution of lambda to the k. So it's the kth moment. And of course, if you know all the moments of a probability distribution, you know the probability distribution itself. You can characterize equivalently a probability density in terms of its expression or of its moments. Okay, and there is a one-to-one correspondence between moments and probability distribution. So this formula tells you that somehow, even if this is through this implicit relation, in the sense that, I mean, this tells you that the Stieltjes transform contains the information about all the moments of the spectral density and therefore contains the spectral density itself. You should be able to rederive it from the Stieltjes transform. Of course, in practice, imagine that you know this Stieltjes transform. There is some God that gives you a formula for it. You will not compute one by one all these derivatives in order to try to reconstruct the moments. And then, by the way, it's a non-trivial problem to reconstruct the probability distribution given the moments. Okay, this is a well-defined mathematical problem, but it's not an easy one. In theory, you should be able to, but it's not so easy. So this formula is telling you that both objects, the Stieltjes transform and the spectral distribution, are somehow equivalent, contain the same information, but this formula is not so useful. You cannot use it concretely to reconstruct rho from J. Okay, so we need something else, and this something else is called the Stieltjes inversion formula. Okay, so this is the key connection between the two, and the reason why, once we know G, we can get H in a concrete and useful manner. Okay, so let's see what this formula is telling us. This formula is telling us that if you know the Stieltjes transform associated with the spectrum of a random matrix, when this random matrix has been taken to be very large. So really, this notation you see with an H which is not bold, like for the spectral densities, emphasizing that this H is not anymore a fixed matrix. We have taken the system very large, so this G only depends on the distribution of the eigenvalues, okay, of the associated random variable, which is this infinitely large matrix. Okay. Okay, so this formula is telling us that if we know the Stieltjes transform, let's evaluate it in lambda minus a small imaginary part. Epsilon is positive, is a small positive real number. So I remove a small imaginary part to lambda. I take the imaginary part of this complex valued function. I divide by pi, and I take this imaginary part going to 0. Or it goes to 0 plus with a minus. So this goes to minus 0. It's an imaginary part coming from below, going to 0 from below. And this gives the spectral density. So this looks a bit, looks like a weird formula. Where does it come from? It's not so evident why this would be true, but actually the proof is very simple. So why not doing it? Okay. Before proving this, yes.
I was just going to add, it looks very similar to the, so if G is the polarizability of like a molecule, then rho is the cross section. And actually we have the exact same formula.
Okay.
It's 1 over pi, the imaginary part of the polarizability, slightly shifted.
So I guess that there must be a fundamental link with the RMT, yeah.
Yeah, it seems interesting because the G is like a green function. That's what I'm kind of conceptualizing.
Yeah. True, and actually, even in random matrices, sometimes people call the resolvent or the Stieltjes transform the green function. Yes.
Oh.
Yeah, it is connected. Yeah. Thank you for the remark. So, yes, please go ahead. There was a question. I've heard someone.
Is there any question?
Okay, I guess. All right, so let me prove this formula. It's very simple. so it's worth doing it. So the way we're going to prove it is just verify that it's true. So we're going to start from the right-hand side and verify that this identity recovers the spectral density. Okay? So let's do this. So if you write down the Stieltjes transform of lambda minus epsilon and take the imaginary part, it gives this, simply by definition. I'm taking the imaginary part of the definition of the Stieltjes transform evaluated in lambda minus I epsilon, and this average there is part of the definition, right? Because the J of lambda okay, so I'm using just the definition. And this equality is just by multiplying the numerator and the denominator by the complex conjugate of the denominator. The denominator is a complex number, so I don't like to have a complex number at the denominator, so I multiply the top and below by the complex conjugate. So what appears at the bottom is the norm of this, is the modulus of this complex number, and the imaginary part of the complex conjugate of this is indeed just epsilon, right? So I have my epsilon that appears here. Perfect. And what you recognize here now inside the integral is called the kernel. It's this kernel. So sorry, someone has the microphone on and it's a bit disturbing. Okay, thank you. So we have this kernel that appears here, which is called the Poisson kernel. It's just a function. And the thing is that this object, this integrand there, tends to a delta function when epsilon goes to 0. Okay, so this you can verify. Let's try. Sorry.
Please switch off your mic, everyone. Okay, let me just mute it for all. Huh?
I just did. Thanks. So this object is an approximation of the delta of the Dirac function. Okay, of the Dirac delta function. So you see, indeed, if epsilon goes to 0, assume that lambda is different than mu, then whatever this difference is, at some point epsilon will be much smaller. So this term will win against that one. And so all this will tend to 0. Okay? Instead, if lambda equal mu, this term is not there. And what we obtain is 1 over epsilon, which explodes when epsilon goes to 0. So it's indeed an approximation of the delta function, right? It's an approximation of delta times lambda minus mu. But there is an additional pi, because this delta function is a well-defined probability. It's the integral of it is 1, while the integral of this Poisson kernel is not 1. It's 1 over pi. So you need to normalize it, and this is how this pi appears. Okay? So that's it. So now you take epsilon going to 0. This gives us the pi delta, and the delta function peaks when I integrate the delta function against mu. So essentially this is equal to pi delta lambda minus mu. And so when I integrate against mu, it will enforce mu to be equal to delta. And so I obtain this thing. And that's it. The proof is done. Okay? So very simple, but very useful formula. Okay? Is there a question before I move on to now how to derive the semicircle law for the GOE ensemble using this formula?
Any questions?
Okay, if there's not, that's fine. So now we know that if we have access to the Stieltjes transform associated with a random matrix ensemble, we have access to the spectral distribution. Okay, so what I claim is that we know the Stieltjes transform for many ensembles, in particular the one for the semicircle distribution is this one. Okay, so we're going to derive it if I manage to arrive there. So this is the one for the semicircle, and this is the one for the Marchenkov-Pastor distribution. So they're a bit obscure formulas. It doesn't matter. This is just a function that I'm giving to you. It has a certain form. But now I claim that if you use this and you plug it in this formula, there, you will reconstruct the semicircle distribution. Okay? And this is done here. I will not do it. You can try. It's an exercise. You have to be a bit careful because the square of a complex number here, and then you have a square root. So you have square root of complex number. You have to be a bit careful, in particular for a complex number. Tau, its square root is given by this. So it's you have to be careful with this formula. But once you know this, you just use it in the formula above, in the Stieltjes inversion formula, and you will find the semicircle distribution in just a few lines. The proof is this. Okay? So do it. That's an exercise for you. Okay? Perfect. So this is just a computation. It's not so interesting in itself. It's just manipulating complex numbers below a square root. So it's there is nothing so interesting there. So you can do it by yourself. What is more interesting now? Yes.
A quick question. Yeah. So let's recall. So what's lambda again? So lambda is the.
So lambda.
The
yes. No. It's not a coupling. Lambda is just an argument. Lambda you mean in what? Where?
Yes, the rho lambda, g lambda.
Lambda, g lambda.
Yeah, in the last expression you just highlighted. So what is that lambda again?
This lambda represents a possible eigenvalue of the matrix that you're studying.
Yeah.
Lambda lambda means eigenvalue. So this row of lambda is the probability distribution of eigenvalues of a certain random matrix. Okay? In the limit where this random matrix is very large. Okay, so it's an argument. This is a probability distribution.
Mm-hmm. So what does g of lambda then say? So if I have, I'm trying to think of it in the context, I don't know, maybe this is limiting my intuition, but I'm thinking of it as g lambda like a polarizability.
Like a
g
what?
lambda is universal, like a polarizability. Like, does it mean the semicircle law is always -2 to 2? Like,
The semicircle law is this, yes?
Yes, exactly. It's always -2 to 2. Or that lambda, regardless on the matrix size, it's always going to be
There is no
-2 to
more
2.
matrix size. You see here, I've taken the matrix size going to infinity already.
Exactly. Okay.
Yeah.
Perfect. And so, yeah, lambda is just that x-axis.
It's just the x-axis, exactly. So I'm scanning through all the possible eigenvalues, and this row is telling me what's the weight, the probability weight, the density of eigenvalues around lambda. Yeah.
Exactly. Okay.
Okay.
Yes.
Perfect. Instead, the g of lambda, this Stieltjes transform, does not have such a simple interpretation. The g of lambda really should be understood as the moment generating function associated with the probability distribution, which is rho of lambda.
Yes.
Okay?
Yeah, so Z doesn't really have a clear
I mean,
so yeah.
Yeah. If you have a, yeah, it's, I don't know how clear is your intuition about what's the moment generating function.
I'm familiar with moment generating function is, yeah. I'm in the context of like it's the Fourier components for that, but then there's the CGIS transform, which I guess is similar to like a Fourier transform. But it's different. And so Z is that transform variable.
Yeah, it's a Fourier transform in the sense that it's a change of it's a bit like a Fourier transform. You're going from the space of eigenvalues lambda to the complex plane Z, and working with this function in the complex plane is easier. Like when you go to Fourier space, some things are easier to compute in Fourier space. Then you do your computation in Fourier space, and you go back to real space by inversion. Here's the same. It's easier to compute the Fourier transform if you want the Stieltjes transform. Sorry, and then you go back to real space, to eigenvalue space, by this formula.
And so then how did you derive G of Z? Because then your derivation then just kind of gave G of Z.
Yeah. It's what I want to do now. I haven't told you how to derive G. So now I want to explain how to derive G. At the moment, I assumed that G could be obtained somehow. Okay? So what I told you is if you can get G through some oracle or some method that I haven't given, you can reconstruct the spectral density. Okay?
Exactly. Okay.
Now I want to explain to you how to get G, which becomes the key question. Okay?
Exactly. That's the question.
Exactly. Thank you. So that's what I'm doing now. So here I haven't done the computation on how to recover the semicircle law given G, but it's just a very simple computation. So this any of you can do it. It's just manipulating complex numbers. Okay. Perfect. So now the question is the derivation of the Stieltjes transform. So thank you for the introduction. It was exactly this. Okay, and I'm going to do it for the GOE ensemble, but the method that I'm going to show you is much more general. It applies to a very broad ensemble of random matrices that are more complicated than the GOE. You can do that, for example, the next simplest example is the Wishart matrices, and you can derive the Stieltjes transform of the Wishart ensemble by the same method. Okay, but let's do it concretely for the GOE. Perfect. We have 25 minutes. I think it's exactly what we need. So the key method behind this computation is called the cavity method. And cavity method in physics is a generic approach used to derive consistency equations for quantities of interest. So consistency equation means, in general, something of, let's say you want to compute some function, which is what we want. We want to obtain G of Z, okay? A consistency equation is something of the form G of Z equal to some other function f that depend on G of Z. This is a consistency equation. This defines G of Z for every Z. If you can prove that G of Z has to verify such equation where f is known for every Z. So for every Z you show that this has to be true, then this characterizes J of Z. Okay? So this is what I call a self-consistency equation. Okay? It's an implicit solution for a quantity, in this case for a function. Okay, so we want to derive such a consistency equation. And a generic approach to do so is called the cavity method. Okay, so let's see how it works in the context of random matrices. So the starting point to apply the cavity method in random matrices is called the Schur complement formula. And this is a formula that is not just useful for what we're going to do now. I advise all the students to really understand what this formula means and absorb it, because it's extremely important in many contexts, in linear algebra in general, and to derive efficient computational approaches to compute inverses, okay, inverses of large matrices. Because of course, as you probably know, computing the inverse of a generic matrix is quite demanding computationally. The complexity, if M is of size n by n, the total number of operations needed to inverse a matrix of size n by n, in general, scales like n cube. Okay? The Schur complement formula is a way to reduce the complexity if you are not interested in getting the inverse of the full matrix, but you are interested somehow in subparts of a matrix, in sub-blocks. Okay? So let's see how. Okay, so let's M be a generic invertible matrix, okay, which we divide in 4 blocks. 1, 1, 1, 2, 2, 1, 2, 2. Okay? These blocks can be of any size that you want as long as the dimensions match. So this M11 block will be of size little n by little n. Okay. Sorry, I haven't noted. Yes. So here in my notation, this matrix is of size t by t. Okay. So the first block there will be of size little n by little n. The block 1, 2 is little n by little n minus t. Then 2, 1 is n minus t times n, and the 2, 2 is n minus t, n minus t. So the matrix looks like this. There is a block there. For example, it could be like this, okay? And this would be n by n, n minus t, n minus t. And we have our 2 blocks, 4 blocks, sorry, 1, 1, 1, 2, 2, 1, 2, 2, okay? Let me just, for convenience, call the inverse of M Q. And I can induce the same decomposition in Q. So I have again my 4 blocks, which are of the same size as for M. Okay? Perfect. The Schur complement formula tells us that the inverse, the block 1, 1 of the inverse of Q, okay, is given by the following. So, excuse me, now I think I wrote a typo there. Q. No, this is correct. So, the, no, one second. Inverse of Q block 1, 1 and M1, 1. No, wait, I have a typo. Let me double check. Excuse me. Just give me one second. Yes, no, okay. excuse me, so here I will correct in the notes. This is I put the parenthesis at the wrong place. This is Q11, the first block of Q, inverse, and not the first block of the inverse of Q. Okay? So, the formula tells us that the inverse of this block can be related to the blocks of M. And you see, we have M11, M12, M21, and the only inverse that appears is the M22 block. So you see that if you are only interested in obtaining the inverse of a subblock of a matrix, you can avoid inverting the whole matrix. You can instead use this matrix, and the only inverse you will need to compute is the one of that block. Okay? So you see, you want to get information about the inverse of that block, you only need to compute the inverse of that one. So you will gain, because you see, now you need to invert something that can be a much smaller matrix, depending on what little n and t are, but you will gain in computational time. Okay? Perfect. So this looks like a generic linear algebra result. Very nice. So let's see how to use it. Why is that useful for random matrices? Is there a question on this formula, or is the meaning okay? Okay. I hope it's fine. So let's see how the cavity method works. Consider H. So now I will index H by its size, because we're going to work with matrices of different size. So just to make that precise, Hn will be a GOE matrix, so symmetric Gaussian matrix of size n by n. Okay. Let me define capital M as Z identity minus Hn. And so what you recognize here is, of course, that M inverse, Mn inverse, is the resolvent. Okay, the inverse of this is by definition the resolvent. Okay, that I will call GN. Perfect. So if I now do a decomposition of this matrix M in blocks, isolating here on the corner just the first element. So basically I'm decomposing my matrix M. So it's a square matrix as just first element, first column, first row, and all the rest. Okay? And I'm applying the Schur complement formula on this decomposition. Let's see what happens. If we use the formula, so it tells us that the inverse of the first block of the inverse of the original matrix, so the M, you see, and this is the same as M inverse block 1, 1 inverse. Okay? So if you use this, you realize that on the left hand side you just get the element 1, 1, the first entry of the resolvent, because the element 1, 1, this is indeed M inverse element 1, 1 inverse. M inverse is the resolvent by construction. So this is the first block of my resolvent, which is a scalar because I've isolated just one scalar, so it's a matrix 1 by 1. And I take the inverse of this matrix, which is just a scalar, and so it's the usual inverse. So I obtain this. Okay? And on the right-hand side, I just apply again my show formula. So this is my first block there, my M11, minus my M12, which is there, times my M, the inverse of M22, and the inverse of this block is the resolvent there. That is the resolvent for a GOE matrix of size n-1 now, times my M21, which is there. So this is a direct application of the show complement formula. Okay? And why is that useful? Because you see, this looks already very much like a consistency equation. Not really, because on the left-hand side, I have something which is related to my resolvent. On the right-hand side as well, but it's not exactly the same resolvent. Here, this is the resolvent for the system of size n, or a matrix, a GOE matrix of size n, while this is the resolvent for a GOE matrix of size n-1, right? Because indeed, this matrix, by the way, is just a GOE of matrix of size n-1, right? If you take a GOE matrix and you just take a subblock, you take a GOE matrix here, the subblock there is itself a GOE matrix with the same statistics, but just of size n-1, okay, by definition of what a GOE matrix is. So I have an equality that relates the resolvent for the system of size n and the one for the system of size n-1. So it's not yet a consistent equation because I don't have the same on the left and on the right. But now I'm going to use the fact that when n becomes large, these two objects, somehow they should be the same. Because when n goes to infinity, whether you look at the matrix of size 10 billion or 10 billion plus 1, it should be the case that somehow their resolvent are essentially the same. And this is the case. Okay? So let's make this argument slightly more precise. I cannot prove every steps, and I will ask you to trust me and to check the references that I'm mentioning there. But I give you the main idea. So let's now, from this equation, derive a self-consistent equation for the Stieltjes transform. So the first thing to notice, so now we are considering that n is going to infinity. It's becoming very large. We're considering a sequence of problems of increasing size and trying to understand what is going on using this equation and simplify it when n goes to infinity. The first thing to notice is that this vector v, what is this vector v? By construction of our, remember, m is z minus a GOE. So basically, we are just shifting the diagonal of a GOE by z, right? So that's why we have this z minus h11 there, because h11 was on the diagonal. But this vector v corresponds to the elements of minus hn, which have been untouched by this z. So they are just Gaussian variables, independent of everything. This is just a Gaussian vector, right? This is what I'm writing there. This v is just a Gaussian vector independent of everything. In particular, it is independent of the elements of this mn-1, which is itself a smaller GOE, okay? And there is an important property to, you can prove it also in one line, you can try. But if you sandwich any matrix, actually, by a Gaussian vector independent of that matrix, you look at the quadratic form V transpose G V, whatever is this matrix there, as long as it is independent of this Gaussian vector, this is approximately equal to the trace of this matrix divided by n, okay? When we take this Gaussian elements in V with a variance 1 over n, this is why the 1 over n appears. sandwiching a matrix by a Gaussian vector and computing the associated quadratic form, output the trace, okay, by independence of this Gaussian vector from this matrix. So this is an exercise, you can try to show it. So this object, when n goes to infinity, is very large, is very close to the trace of this resolvent divided by n, which is very close, by definition, to the resolvent, to the Stieltjes transform, right? Remember, the Stieltjes transform was defined here. This is the definition of the Stieltjes transform. What I'm claiming is that when n is sufficiently large, instead of having an equality here, you don't take the limit, you have an approximate equality. Okay? And even if you do not take an expectation there, this is still fine, because you have what we call concentration. This object is a random variable, but because it's like an average, it's the average, it's the empirical average of the eigenvalues of this matrix. It's like the law of large numbers. Empirical averages tend to the statistical average, to the expectation when n is large, like the law of large number. So you have a kind of law of large number there, and so whether you consider the expectation here or not, this is not so important when n is large. Okay? So we have this identity. This term here is essentially the Stieltjes transform when n is going to infinity. Okay? Now, let's look at this term there. What can we notice? We can notice that this z is a generic complex number, which is, let's say, order 1. It's independent of n. And instead, this random variable, h11, what is this law? It's the diagonal element of a GOE matrix. So it's a Gaussian variable with variance 2 over n. And when n goes to infinity, this Gaussian variable concentrates onto its mean. So it's very, very close to 0. So we can neglect this quantity because it becomes very small compared to z. Okay? Perfect. And the third ingredient that we need, we have already simplified quite a bit. So with these two equations, we obtain what? We obtain that 1 over g n z element 1, 1 is equal approximately, and let's say, yes, when n is very large, to z minus the Stieltjes transform evaluated in z. So now I claim that also the left-hand side, actually the denominator, is G itself, is the Stieltjes transform itself. We have shown this identity. So in particular, it tells us that the left-hand side is not a random variable. It has to also concentrate. So it means that the diagonal, any diagonal element of the resolvent of a GOE matrix is not a random object. When n grows to infinity, it tends to a constant, which depends on z, but it tends to a non-random object. This is again concentration. But now I claim that this constant does not depend on which diagonal element you are considering. And this is a consequence of the rotational invariance of the Gaussian orthogonal ensemble. You see, by rotational invariance, the law, what we have said at some point is that a GOE matrix is equal in distribution to any rotation of the same matrix. So this equality in distribution means they have the same probability distribution. And in particular, a special type of orthogonal matrices are the permutation matrices. I can choose a O, which is a permutation, which will change the order of the diagonal elements of my H. Okay? And the law should remain the same. This property extends to the Stieltjes transform, to the resolvent matrix. The resolvent matrix has the same, essentially the same probability as a GOE. The only thing we have done is to shift its eigenvalues by Z, and then we took an inverse. But the law of the eigenvectors is the same. So all that to say that by rotation invariance, if you change two diagonal elements of this resolvent matrix, it has the same law. It means in particular that any diagonal element have the same mean, the same expectation. And because the diagonal elements are equal to their expectation, because we have shown that they are non-random, it means that this G and N I are all equal when N is large for every I. So it means that the diagonal of the resolvent becomes a constant when N is large for the resolvent. And in particular, if they all become equal, they are equal also to the average, the empirical average over diagonal element, which is trace of Gn over N, which is again the Stieltjes transform. Okay, so using all this, what we obtain is that the left-hand side is 1 over the Stieltjes transform, which is equal to Z minus the Stieltjes transform. So we have obtained the self-consistent equation. We have characterized the Stieltjes transform by the cavity method. And so now that you have this equation, you can solve it. And the so it's a quadratic equation. Okay, you can multiply the left and the right-hand side by G. You obtain this quadratic equation. And so you solve it explicitly, it's a quadratic equation, and you obtain the semicircle law. Okay? So why is this called the cavity method? Or leave one out? Because you see the starting point is really that we extracted one diagonal element of this matrix M, and then by the Shor complement formula, we related the inverse of this single diagonal element to the inverse of all the rest here. So we have kind of extracted a cavity in the system. We've done a small hole, which corresponds to extracting this element, and compared that, related that to all the rest of the system. So it's like digging a cavity in the system and seeing how the system reacts, changes. And because the change has to be small, this is what we exploited there. Okay, these are these are consequences of this change being small. You can close an equation on the Stieltjes transform in this case. Okay, so it's exactly 2. So I think this should be the end of the lecture. I know it was a bit dense. I hope you understood at least the main idea. And the main idea is not complicated. It's really just comparing the system of size n with the slightly smaller one, n minus 1. And the relation between the two is this Shor complement formula, which allows to close an equation on the Stieltjes transform. Is there a question?
Do we have any questions?
What is the benefit of using this approach for I cannot visualize the long-term advantage of this method.
The advantage in what sense?
See, we try to identify a cavity and then try to trace it for the rest of the system. So, why we did it? Like, what is the motivation behind that?
The motivation is because it's the only way to find an equation for the Stieltjes transform. So you see, the Stieltjes transform is related to the trace. It's related to the trace of the inverse of this matrix. Okay. You cannot compute this directly. You need somehow to find an equation that defines it. So basically, you see, what you have somehow is let me try to say it in another way.
So if I'm not wrong, is it some way of like induction method? Like we try to solve it for some part and then
Yeah, it's similar.
It's exactly like an induction, if you want. So if you want, what you have is this. So you have n inverse, and if I take then 1 over n. So what I want to compute is this, but this is just the definition. So trace of z. And here I'm stuck. I don't know what to do because I cannot compute this explicitly. So this is just the definition, if you wish. Somehow, if I want to make progress, I need to force the same object that I have on the left to also appear from the right. In this way, I will have an equality between something and itself. I will have a relation for the object that I'm interested in. And to find this relation, I can exploit this show complement formula. And from this characterization, from this definition of the Stieltjes transform, I will have the Stieltjes transform that appears again. It's an induction, like you say. And so I can close an equation. It's like this.
Okay.
Okay?
Okay, sir.
Thanks.
Do we have any other questions?
Yeah, I'm just trying to understand why. So the Stieltjes transform, yeah, it's nice. This way of deriving that g of z. However, you can't do this in real space. That is to say, if you have a Hamiltonian matrix, and then you have a submatrix of that and obtain the spectrum, you can't relate it in the real spectrum in some inductive way.
No, you cannot, because you don't. The key point, what allows to get a self-consistent equation is that you have this per block inversion formula. You can relate inverses of smaller blocks to inverse of a bigger matrix. But now if you directly try to relate the original matrix and its spectrum to the spectrum of a matrix from the same ensemble but slightly smaller, you don't have an equation to connect them. You don't have the equivalent.
Yeah,
That's the whole point.
The scale matters.
Yes.
Like I said, with very small, like I'm not even thinking about using Stieltjes transform. I'm just saying use the random matrix directly and trying to obtain that spectrum
there
density.
is no obvious way. There is no obvious way how to do it.
Okay. I'm just trying to understand. Yeah.
No, but it would be. It sounds like a more natural approach to try to find directly a self-consistent equation for the spectrum itself. It sounds very reasonable.
Yeah, but there's no. It loses scale invariance though, because then, like I said, when you have very small matrices, then that spectrum is completely unrelated to the infinite.
Exactly. That's exactly the point. But here, because if you want, the fact of working with inverses, the inverse is an operation that mixes all the elements of the matrix in a very non-trivial way.
Exactly. Yeah,
and
exactly.
This mixing induces concentration, even for smaller matrices. So this mixing operation, this inverse operation, is very important to have all the necessary concentrations that allow you to close the argument. While indeed, if you look at small matrices, you don't have concentration of the spectrum and things like this. I mean, I think we're saying the same thing.
Yeah, unless you have thought of like, okay, if you have a small matrix, but it's interacting with the rest of the matrix in some way, maybe there's some hope. Like it's perturbing the spectrum of that small matrix.
Yeah, maybe
In
that
the
way.
cavity way.
Yeah. Maybe it's possible. I don't know. I know that the standard approach is to go through the resolvent. Yeah.
Exactly. Yeah.
Okay. I would like to express my sincere thanks and gratitude to Jen Barbier, to all the participants, to Julio, Arpita especially for showing their attentive participation, and I thank everyone for their patient hearing.
Thanks
Thank
a
you.
lot. So we'll meet again tomorrow.
Okay, yes.
Thank you, ma'am.
Thank you, Arpita. Thank you, Dr. Julio.
Goodbye.
Thank you.
Bye-bye.
Bye-bye.